This will be just a short introduction to surface gravity waves. The class will have some other video snippets from YouTube discussing some phenomena associated with surface gravity waves, such as refraction. Waves, this is just a generic slide about waves. There's different types of waves: sound waves, light waves, we believe, wind waves, capillary waves, radio, instrument strings, for example. Now, how are these different waveforms generated? There has to be some kind of initial disturbance. So in a guitar, for example, you pluck it with your finger. When earthquakes is a movement of the tectonic plates. In the ocean, it could be wind or gravitational forcing. So the other component you have to keep wave motion is something to maintain these oscillations, a restoring force. When you pluck or bend a guitar string, the tension in the string tries to return it to its zero position, its initial position, and then it will overshoot and then vibrate until dissipation attenuates the vibrations. In the ocean, it will be gravity. That's where we're focused on gravity waves. There are other types of waves in the ocean where the restoring force is not gravity. These are very large-scale planetary waves. Here we're focused on gravity waves. Very small waves, such as when you throw a rock in a pond or trail your finger through a bowl of water. These tiny waves are the restoring force is surface tension. And those are important mainly in the ocean because they give rise to a roughness to the water that allows the wind to take hold and grow larger waves. But for the most part, the waves that matter to us are gravity driven. How fast do they go? Well, they go at finite speed, and sometimes it depends on the medium. For example, tension in the guitar string, depth in some kind of ocean waves, or density. Vibrations in a rod will depend on the density of that rod. Some waves can travel right through a vacuum, like light. Other times, how fast they travel depend on the wave property. These are known as dispersive waves, where that wave speed depends on the properties of the waves. And we'll see that some categories of ocean waves can be considered dispersive. This is just an anatomy of a wave. So this is thinking about a wave snapshot at a fixed time. So it's as if you took your camera out and you took a picture of the wave and then you went back to make measurements of the wave. So these are positional or spatial dimensional quantities. We have our coordinate system, x along the wave and z positive up. We're going to stick with that for the class. Then we have this distance between two successive crests or troughs. In a wave like this, those would be the same. And these can be different things: little lambda, big lambda, capital L, quite interchangeably. Typically you see little lambda or L quite often. The deflection of the wave from the mean value is known as the amplitude. The amplitude is useful because when we're describing the wave mathematically, it ends up being the constant that sort of sits out front. So most sciences, they just refer to the amplitude of the wave. Oceanographers, because in nautical lore, people have always referred to wave size via the height being the distance from the trough to the crest. And in a small amplitude wave like this that could be described with a sine or cosine function, that is twice the amplitude. That height is a commonly h, capital H, and just keep that in mind. This height and amplitude are both describe the size of the wave, but they are different quantities. We also have the wave number, k, which is the number related to the number of waves in a specified distance. You can see it goes as 1 over the wavelength. So these are all spatial dimensions, positional dimensions. If you stood at one place watching a wave go by, so this is a fixed location, fixed observer, and they watch the wave go by. Now you're talking about a crest going by, then a trough goes by, then a crest goes by. So this becomes time on this axis, and the time between two crests is a constant, t, which is the period. That's the time between successive crests. It's a unit of time. And we also have frequency, which is the number of waves in a given time period. So that's 1 over t. That has dimensions of cycles per second, which we also call our hertz. And then we have the angular frequency. Omega is 2 pi over t. And this is radians per second, time between successive crests. So it's 3 ways to describe the same thing. We can convert between them. Omega equals 2 pi f, for example. These find their way in the mathematical formulas. This is the easiest one to think about because it's more intuitive. What's the time between crests? Ocean waves have one additional key factor, which is this, the depth. Usually noted as the depth, the distance from the ocean floor to the mean wave height. So it's an additional dimension that will play a role in some waveforms. For ocean waves, as I mentioned, the restoring force is gravity when they're large enough, so capillary are very small waves, and there's a class of waves known as planetary waves, which we'll discuss later in the course. But in terms of tides, down to wind-driven waves, it is all gravity. Some kind of initial perturbation, astronomical forcing, that we'll talk about tides, ships going by, the ship wake as water waves, gravity waves, wind blowing, seismic, think about a tsunami. There are 2 key ratios that control the dynamics. One is this one here, very important. What is the depth related to, divided by the wavelength? So the ratio of the depth to the wavelength. And the other is the wave height divided by the wavelength. And this is a measure of how steep the wave is. If the height gets bigger for a given wavelength, so this wave is the same wavelength as the other wave, but you can see how steep it gets as h over L gets larger. So steepness will play a little role, particularly in nonlinearity, and there are limits to how steep a wave can get before it breaks. This idea of the energy spectrum in the ocean, so we have it broken down here at the bottom in terms of period. So you have swell and wind waves, so these are wind-driven waves here. And they're on the order of 10 seconds, 20 seconds, 30 seconds, 4 seconds, 3 seconds. So seconds or tens of seconds at the most. Then you have a gap. And then in the gap are these very, very rare tsunami waves, where you have periods on the order of hours. But they're so rare that they don't account for much energy in the ocean. And then you have the tides. The tides come in these very discrete periods that are related to the periods of the astronomical forcing. So they have these little peaks that you see here, and these are all in the order of hours and days. And then you have the planetary waves, which move on the order of weeks, months, etc. So this is period getting longer, and you can see how the energy is compartmentalized in these different phenomena. We're going to be focused in this lecture on gravity waves up to here, and we'll have specific units later on tides. So right now we're focusing more on wind-driven waves. So the wave solution has a nice history to it. I can maybe put up a nice document I saw. Mathematicians try to tackle the problem of mathematically describing water waves over the years, and this we're talking 1500s and up. And the various people came along and they made proposals and they made certain assumptions. And back then news traveled slowly, and you would go present your paper at an annual meeting with your long beard, and it wasn't until 10 years later that someone picked it up and realized you had made an error or an improper assumption, and then around it went again. So Airy really came up with the first one that wasn't problematic, mathematical description of a wave. And essentially what he did is he took the governing equations for fluid flow, which we call the Navier-Stokes equations. Then he made a couple assumptions, that the fluid is irrotational and viscid. That greatly simplifies equations into what we call potential flow. Then he decided the wave is linear. It has small amplitude. The amplitude to length ratio is very small, and that allowed him to treat the boundary condition as a flat surface. and then, or the wave boundary condition is a flat surface, and then he made an assumption about the nature of the shape of the wave, that it was a cosine function, that you could describe the free surface shape as a harmonic function. Once he did that and applied the boundary conditions, he came up with a closed form solution for his wave that was dependent on wavelength and depth and other factors. And the key thing is this h over L parameter. This h over L parameter decided the character of the solution, affected entirely the character of the solution. So I won't put the equations up here. It's just a bunch of sines and cosines for the velocity field, pressure field, and free surface height multiplied by hyperbolic functions, and those hyperbolic functions are varying strongly with this h over L parameter. It showed up everywhere. So what we do is look in the limits of h over L. So when h over L is big, that means it's very deep compared to the wavelength. And when h over L is very small, that means it's very shallow compared to the wavelength. Or conversely, the waves are very long compared to the depth. In those two limits, you have two very different phenomena. Keep in mind there's a gap between the limits, what you call transitional waves, and in there you can't speak strictly one way or the other. You have to deal with a true nonlinear solution in order to say something about the what the wave is doing. But in these two limits are informative because a lot of waves can be classified within these two limits. The first is the deep water limit. So in Airy solution, what you find is that the wave is moving and the water is moving in these orbital motion here. So if I were to put a neutrally buoyant ping pong in the water, it would just sit there and form closed circles as the waves pass by. So it's important that if you put material on the surface, it doesn't actually travel with the wave. It oscillates back and forth. And in this theoretical and viscid solution, it'll just oscillate back and forth till the end of time. It doesn't actually move with the wave itself. In reality, there are processes that cause some drift, we call Stokes drift, so very slow drift, but those were not accounted for in Airy's formula. In Airy's formula, they were forming close orbits, and they were circles, that had orbits that decreased with depth. And when they got to a depth of once they got down to a depth that was equal to 1/2 the wavelength, the orbits are essentially zero. Now it's an exponential decay, so they don't go to zero until you get to negative infinity. But we consider them cut off at a 1/2 L. Below that, so if you're a diver and you're here, you can feel that wave going by. If you're a diver and you're here, maybe you see changes in light and such, but in terms of pressure sensation, you don't feel anything. That's because you're below this wave critical depth here of a 1/2 wavelength. If the water's deeper than that 1/2 wavelength, or 1/2 L, or 1/2 lambda, then the wave is acting as a deep water wave. It doesn't know the bottom is there. The bottom could be here, or the bottom could be 1,000 meters below that. The wave doesn't care. It's not affecting its characteristics. It's living essentially in the surface layer, the 1/2 L layer. That's where everything's happening. So the water's moving these closed orbital motions. They decay with depth, and they were pretty much decayed by the time you hit 1/2 L. For these type of waves, the wave speed is given by root g over k, or if you want to write it in terms of physical length scales, we have root gl over 2 pi. So we see basically it's proportional to the square root of L. The longer wave goes faster by the square root of the length of the wave. These are dispersive waves. What this means is that if you have a group of waves, the longest waves travel faster than the shortest waves. We call this frequency dispersion, meaning that the properties of the waves are affecting their wave speeds, and they're going to sort themselves out by size. So it's like having a box, and you have a box of mice basically, and you scramble a whole bunch of mice together at different ages, and the older ones run faster, and then you let them run around the room. The fastest ones are going to spread out first, faster than the slowest ones. They disperse throughout the room. So the same thing happens with our water waves. The longer waves travel faster, and it goes as the square root of the length. And then we can make this connection between period and the wavelength. via that relation, because the wave speed can be written as L over T. How far it travels, length in a given time, is the wave speed. It's a velocity. So that's, again, so this is when h, the depth, is greater than 1/2 L. We have a deep water wave. Sometimes it's called short wave because the waves are short compared to the depth. It's more common to call it a deep water wave. It depends how you look at the limit. The other limit is the long wave limit, also known as shallow water limit. This is where the depth is very small compared to the wavelength. It's smaller than a 20th or 5% of the wavelength, or we can think of it as the wavelength is greater than 20 times the depth. In this limit, you have elliptical, actually linear motion at the bottom here, along the bottom, still forming closed orbits, but the key thing is the wave feels the bottom. The wave is interacting directly with the bottom. There's, again, no net motion of the particle. That's the same. And the z extent always decays with depth. The fact that the wave is inducing motion right at the bottom means that it can make a stress, just like wind blowing on the surface of the water makes a stress. The currents moving back and forth on the bottom can induce a stress and suspend sediment. This is waves can suspend sediment. The key thing finding here is that the wave speed is dependent on the depth, not on the wave characteristics. So if we've decoupled T and L, the period and length are decoupled. The speed, C, or celerity in a wave, the speed of that wave depends only on the medium, the depth of the water, root GH, and G we can't affect. So it goes to the square root of H. Deeper water move faster, shallow water moves slower, but it doesn't depend on the wavelength. So a short wave and a long wave can travel right next to each other at the same speed, provided the water is shallow enough, provided we meet this criteria. So obviously there's a cluster of waves between these two criteria when the water is too deep to meet this criteria but not deep enough to meet the other. Those are what we call transitional waves. This is a summary of the wave celerity diagram. If I think of a wavelength of 10 meters out here at 800 meters of water, this is the depth on the x-axis, that is a deep water wave. The deep water wave doesn't care how deep it is, so the speed, which is this axis here, the speed is the same for this wave because it's a fixed wavelength until you go to shallower and shallower and shallower and shallower until it starts feeling the bottom. Excuse me. When we hit this dash line, that means it's starting to feel the bottom. And this is the nonlinear transitional zone here. And then eventually it will merge into this line here. This line is the shallow water wave speed equation. Basically, the wave speed is a function of depth. That's saying y, which is our speed axis, is a function of h, our x-axis. That would be the same as writing y equals the square root of gx. Actually, not quite, because this is a log display of that. But we have, actually it's written so we end up with a straight line with our square root. So we have a straight line relationship here. This also shows you that the same wave of a fixed wavelength travels faster in deep water, and as it approaches shallow water, it slows down. All these curves for a given wavelength slow down as they get towards the shallow water wave limit. So in shallow water, waves are slowing down. They're interacting with the bottom. Wave power generation is becoming a popular topic. I've put here four different popular types of wave generators. This is called a limpet type system. The water basically comes in. It's difficult to see, but this thing here contains the water. Air lives in there, and as the water comes in, it compresses air. The air moves through, and it turns this turbine right here and generates electricity. So you're compressing air on each wave, and as the water goes out, it pulls the air the other way. So it's a two-way turbine driven by the air, which is driven really by the water being forced into this box. Obviously, there's a big coastal presence. So yeah, good luck getting these approved for your beach, but you do find them in various places. The UK has some of those. This is a sea snake made by Palamas down here. Off the coast, there's an installation off the coast of Portugal. It's obviously an artist rendition, but it looks pretty much like this. They don't have as many, but it looks like this. Here, basically, you can think of it as if you have a stick filled with very high pressure hydraulic fluid, and you bend it. So think even like a garden hose you cap at the end, has a lot of pressure in the line. If you bend it, in bending it, it increases the pressure in the line. You can use that pressure to do work, but you had to expend energy to bend it. Here, as the waves are going through, they're bending and flexing this Palamas sea snake, which is bending the internal hydraulics, which are being used to generate electricity. These are point absorbers. These are typically seen in deeper water installations. Right here, you can generate electricity through induction. So you have a magnet here, and you have a body that's floating up and down with the waves, moving back and forth across this motor, across the coil, in order to induce electricity. So they move up and down, and they're good for deep water sites because you just need to anchor them floating to the bottom, something we know how to do. Near shore, this is a popular style here, a flap style wave power generation, like the Aqua Marine Power. This is their Oyster product. Actually, they have a different looking one now. But the idea is it flaps back and forth as the wave diffracts around it, which isn't very well drawn in this, to be honest with you, but the wave diffracts around it. You have a lower free surface on the back than you do on the front, and that will generally power up this device. So this is what you're seeing. Now, how much power is in the wave itself is given by this simple equation here. Significant wave height squared. So it goes as the wave height squared times the period times this constant factor out front, which is not much you can do to adjust. This is units of watts per meter. So if you think about a wave crest here, let me just erase my sketching here. A wave crest here, let's say that wave crest is about 10 meters long. The watt, and we knew the characteristics of the water at this moment here. I don't know what the period is here, but it looks like several seconds, maybe 5 seconds, maybe a meter wave height. You plug that in and get your power per meter, multiply it by the meter long wave crest, and that gives you the power that these waves are providing. Then you have to look into how much you're actually capturing, which can be far from 1. But there's a lot of promise to this. One of the things that some of the companies are targeting, particularly in devices like this, they can be mounted near shore. Now this flaps back and forth, and you would do the same thing. You would have a power takeoff thing, a hydraulic system that led to power generation. But the other thing you can do is just use that hydraulic system. Instead of pumping hydraulic fluid through a generator, you can pump seawater through a reverse osmosis system to generate fresh water. And so there's some companies targeting that in areas that have lots of waves and not a whole lot of water.